say is that there's a big team of people in any of these jobs, and I'm not going to name everyone, but it's important to note that there's us, Irving Smith Architects, there's RTA Studio, which is another architectural practice in Auckland, and Dunning Thornton, and it really it's a collaboration between all three outfits to kind of get here. The project is for Scion, which is New Zealand's Timber Research Institute. So it's where all the timber research happens in New Zealand. So it's a big campus in Rotorua, and the intent of the building follows the campus in that it has a position within its community, and it looks to contribute to its community, but it also is contributing further than that in its science to the region and to Aotearoa New Zealand, and then globally. And so the idea of the building is to previously, when you entered the campus, you were on the outside of a fence. There's health and safety, and it's a complicated thing to enter. This building's outside the fence line. So the ground floor is public and open to anyone to go into. And then above it is 2 floors of science, sort of collaborative space that everyone can see. And so the idea of the building is really to promote timber structural use. And, we kind of use the idea of come walk in our forest, come see what's possible, come see what the future can be, and see where timber can take us.
It's probably a given that it's for, about research and forestry, so why timber was chosen, but part of the brief was to really just push the envelope and innovate in some ways. Is that right?
Yeah, and Alistair should jump in here, but from their point of view, it was important that the building, one, was seen to be legibly timber, and also that it did something new, and that it created, wow, this is where timber can take us. So the idea of, which Alistair should talk about, the diagrid idea, is an instant way of kind of making timber work as a timber building, rather than trying to make a building in timber that looks like steel or concrete, or works like steel and concrete.
So I might move over to yourself, Alistair, if you can start.
Yeah, that's a pretty good segue.
Yeah, great segue if you've ever engineered one.
Yeah, well, we've been talking at our practice for more than 10 years now, having done a bunch of mass timber buildings, about, as Jeremy just said, making these timber buildings that look a lot like modernist steel and concrete buildings, and trying to do it out of wood. And wood's not the best at doing that necessarily, and so there's kind of a period we're all going through is finding a slightly new architecture in timber to best use it. And that's all about the grain, and it's about pointing the grain in the right direction. And we've been wrestling with that on a few projects, especially with our high seismicity over here. When you tend to load things up, which we can with these engineered wood products, you start to have to think a lot more about, for us timber nerds, shear deformations and interlaminar rolling shear and all that sort of stuff that makes it a lot harder to design than just a big block of wood. But really getting the right structural form around that's where we think the Buddha lies. So this was great. I had a couple of architects come and go, hey, we want to do a diagrid, and suddenly the grain's on the angle, pointing in the right direction to both hold up the building and brace it. And so that's where it all sort of started, and we got pretty excited about that. So that was a simple starting point. We got this kind of really rigid building. It's braced. It's all nice. Us in New Zealand, we're very nervous about making things very rigid because earthquakes are very unpredictable. One of my favorite quotes from an earthquake conference a few years ago was that half the earthquakes, major earthquakes that have happened in the world in the last 100 years have happened on faults they didn't even know existed. So it kind of puts the science in perspective. So between that and when we started drilling for the geotech conditions on site, we were looking below 20 meters to found the building, and it was getting hot down there with the geothermal conditions in there. We were kind of like, oh no, this is no place for human beings. So this building perches on this, you know, it's a big dry crust of an ashy soil, but the building needs to be flexible. So if the crust moves, or if it shakes in an earthquake, the building has to move. So we had this kind of tension there. We got this nice, lovely, rigid structure, thumbs up structurally, but then we've got to let it move. So we scratched our heads a bit about that, and came up with the form we've got, which is to create these large diamonds, two-story diamonds out of the diagrid, and then link them with little bits of flexible steel that could take the damage or allow the movement. And so that's kind of where the form came from, and then a few sort of niceties developed out of that. It's an interesting thing with the design process, and I think all of us engineers, even though some of us consider ourselves a bit of timberistas, if you like, we did the first thing that most structural engineers do. We made a node out of steel because we know how to do that. And both Jeremy and Rich and co all said, yeah, we sure we need to do that. And the client then said, does it need to be out of steel? Can we make it out of wood? Because that's our brief to you. And so we had to go and scratch our heads a lot harder. And so instead of making sticks that were joined with steel, we made the big laminated diamond kites out of wood, which we then only needed a tiny bit of steel to link them. We call them U-shaped flexible plates. So it's a tube that's squashed that rolls backwards and forwards in an earthquake. So Jeremy and Andrew have used them before in a couple of mass timber buildings they've done. It's a well-known technology. So we've got almost no steel connecting these lovely big laminated bits of, it's a combination of straight and cross-banded LVL to laminate it up to make the diamonds.
Yeah, looking at the project, one of the balances engineers and architects seem to look for is, you know, being simple where you can and adding complexity. It seems like this project really used complexity in a really, you know, nice way. So if you could both speak about how you can inject complexity like you guys have, and, you know, where the building needs to be simple and a bit different to traditional construction.
Okay, well, I'll go jump in. So clearly there's complexity in the node where the load runs continuously, and I'll let Alistair talk about that. But so from our point, we're trying to make a legible building that has a kind of tells a story, and when you're inside it, you're getting this light condition that changes as if you would inside a forest canopy. In order to kind of get the diagrid, you know, the newness of that idea in the node, the way we work on any of these projects is that we try and simplify as many things to be the same as we can. So that we're not doing gymnastics everywhere, you know, so now let's talk about the node, but in actual fact, the different combinations of, there's effectively 6 different types of diamonds and triangles in this building, and that's not many, and you know, that allows it to be makeable. If we had 126, there's no way they're making it at 26, probably still not making it. So that's one of the techniques, is to kind of put your efforts where it's most important, which is the node.
Yeah, and I think as we found with most of our sort of edgy timber structures we've done over here, the collaboration with the timber fabricator was important. So we conceived a couple of different ways of trying to finger joint these diamonds together. I can go into the node tech in a minute, but it was actually Andrew from Timberlab who came and said, I'm not going to make bits and then finger joint them together. I can just laminate it together in one big diamond on the floor of the shop. And that's a lot easier for us. And it was kind of like the aha moment, because then they can fit it on their flatbed CNC, and they can use the router to clean it up afterwards to check tolerance and stuff. And suddenly all the lights went on. All the last bits we were missing of the puzzle kind of came together. So as usual, it's architect, engineer, timber fabricator, all kind of holding hands.
Yeah, and it is quite a circle. I mean, it's not linear. So I guess the answer to this kind of involvement is it's actually quite a circular, where everyone's sort of pushing and pulling the rubber band a little bit to get the right answer, and respecting what everyone else knows. Yeah.
I mean, the nodes aren't that complicated, but they are to get your head around when you're not normally doing physics like that. So the weakest part of any timber is when you're rolling the grain. So for the engineers out there, you've got your rolling shear that's somewhere between 1.6 and 1.92 MPa, and depending on whether you're on the edge or the middle. So we were trying to make a recipe. We're taking loads down a diagonal, trying to turn them around a corner, tie them horizontally, and then feed them down the post. And so we're laminating up enough layers of grain crossing each other to pull the force across, but to have enough fingers so that as the stress starts to accumulate, you shoot it back down the brace before it accumulates through too many layers of the timber, if that makes sense. So it's drawing those diagrams, it's all it's all hand calculations, which is great. It's actually just getting your head around the concepts. Love that. All the best ideas come that way. You prove it with a bit of a fancy model, but we also proved it by, we made a base joint and a side joint, and we having Scion right there, they made a bit of a jig, and we tested both joints to destruction, just as a bit part of the verification process. So even though we could do the science to show how it worked, it's good to double check that as part of the process. And there's nothing like doing a mock-up to help you think about how to fabricate it and learn a few things, as part of the process.
Yeah, absolutely. And was there an FRL for these details as well to throw a bit of a spanner in the works, or was it no FRL you had to contend with for charring for these connections?
Yeah, right. Fire resistance. The whole building's 30 minutes. So I mean that's sort of our rule of thumb. With if you want to do a whole lot of fancy timber out on show, you kind of got to have a 30-minute building. It's fully sprinkled. It's got a common atria, so it's all one fire cell. So we've got the right kind of building to do these structural hijinks and just rely on charring. Not having steel is great. There's the kind of myth that you can, in the 80s we started knifing in plates into glulam and knew about charring. We said that all worked, and then you look at fire tests, any bit of steel starts to become a hot knife through the butter of the timber. So the whole point is we've got no plates that need fire rating. It's all char. It's all plugged screws, or preferably screws fitted from the top, so there's no head exposed. So letting the wood do what the wood wants to naturally. Again, the floors are held onto the diamonds with a timber corbel, and that's laminated in the shop, and just pinned with some screws. So it's all bearing and charring and all the good stuff that a good Japanese architect would said that we did that 300 years ago kind of stuff.
But that is quite important because the idea that part of the thing about the node is that without the steel plates in it holding it all together, it just removes a massive amount of complexity. So there's more complexity in the node, but around the edges of it, it's allowing the building to have a whole lot of I don't know what the word is, simplicity or ease, like one of those, like an old Japanese. And that's quite a new idea, actually.
Well, it's good design, right? So you take you go to somewhere you need to with complex, and you keep working it until you get a simple solution. And I think we've got most of the way. I wouldn't say it's perfect, most of the way to a pretty simple solution with that. Because the kind of nice thing that we discovered after we didn't, I'd like to claim we thought of this when we imagined them, but we kind of discovered as we were engineering the process, these diamonds with the corbels on each side of them. Not only are we dissipating energy where the diamonds hold hands each side, but because we've got the corbels on the outside of the diamonds, as the building rocks over, it lifts the floor up, and then the weight of the floor pushes it down again. So you got not only a building that dissipates energy and something that you can remove and fix after an earthquake, but it also wants to always right itself. So that was a bit of an aha moment as we were designing it. So, oh, great, we've done something that often we use post-tensioning or other fancy tricks in other buildings, and this one just does it by the nature of its geometry. And again, it's that sort of simplicity of an idea.
At the very beginning of the project, there was obviously the mandate to try and innovate in some ways. What other things were really prioritized at the start, whether it be the culture of the project team or building information modeling or what were the sort of elements at the start that you really focused on that you needed to get right?
We actually won a design competition for a different building for Scion. And if one reason or another that kind of didn't quite eventuate, and then we got asked to come in to do the entry building to the campus. And like you've got to give Scion a lot of credit in that they kept challenging. As a client, they kept challenging for us to come up with this, to chase this all timber junction. And then the idea of the building was we got to quite quickly. This idea of it's all about timber, come inside, come walk in our forest. And that really just necessitated the whole, that led to the design aesthetic of the building. And the timber structure is more important in that than anything else. So those words like legibility and and scale is very important, understanding that we could make the timber smaller. To make a light building, it's important to people coming in and being uplifted and going, I'm interested in this. We could do this. That's all part of the outward message of the building.
And that's really important. Like I've already taken 2 clients who are going, oh, we're pretty keen to do this building, but feeling a bit nervous. It's like, oh, go up to Scion. And, either Scion took them around or we took them around, and they can jump on the floors, and, it's a timber floor. Yes, it feels a little bit more lively, but you can make it very solid. Techniques like a batten and cradle floor and all that sort of thing, they can understand them because they can touch them. And sometimes it just takes that little push to get the client who wants to dive into the kind of timber technology building, but is a little bit nervous about the innovation side. If they can see it and touch it, they go, okay, this is all compliant. I can see that it works. I'm willing to give it a go. And I think that's what Scion aim to do with this building. Yeah. And like we've already been using it for at least 2 of our clients to go and see, if not 3 or 4.
So there's that approach, and there's also, of course, the local, the community approach. That this is a building within Rotorua. So so the buildings, been gifted the name Te Whare Nui o Tutiata, which is a great, which is a great sort of privilege. But that's part of it as a building that didn't need to be public, is opening it's opening itself to the community to come and be involved and come and see what we're doing in the community, and how we have all these people who are working in the timber industry and how it can help. So there's a two-way, but that was the brief. And so if you go there, you can just walk in on the ground floor. It's got a hugely busy cafe. It's got displays. You can go and check it out.
Yeah,
great beer and pizza on a Friday.
Yeah.
A lot of mountain bikers around the area. It's very popular.
It's right at the end of Long Mile Drive, which is, if you go to Rotorua, you'll go to go and do a whole lot of mountain biking and a whole lot of tree walks.
Canopy walks. Yeah.
It's right at the end of that. So it's perfectly positioned to connect, to welcome people.
So the projects had GLT, CLT, steel. I'm sure, all offsite products. Was there a third-party offsite, prefabricator sort of helping putting these together, or was that all sort of put together on site? And is the supply chain in New Zealand got that sort of additional ability to have that additional value offsite?
We worked. We chatted with the timber fabricators early. We got Timberlab involved, and they did all the modelling. They collaborated with XLAM, who supplied the CLT for the floors, and they integrated their model. But what we found, what we did earlier, and we found on our buildings, like for the diamonds and the nodes, we modelled to LOD 500 on the detail. Because if you didn't nerd right into the detail while you were designing it, there wasn't a way that you were not going to have to. You can't solve those problems during shop drawing phase. There's enough to think about during shop drawing phase in terms of how it fits in the CNC, what tolerances are we allowing for growth, and all that sort of thing. So you do have to, as a structural engineer, do a bit more work, I think, at the moment to prove that to yourself that it all fits together. And it's kind of a pleasure, because then it helps you if you go into that level of detail. you kind of get a chance to have another little iteration inside the office. And one of my favorite details on it is at the top of the diamonds, where we've got a linear piece of LVL that just collects all the diamonds, and the linear LVL just dog bones in a tiny bit at the top of the diamond, and it sits on it and holds it in place. The next diamond sits on, and they all beautifully house into each other. And there's just one fully threaded screw down through the whole lot, which is just to pin it in place for sort of builderly means. So it all, it all just kind of clicks together. And that's when you kind of think, oh yeah, we've really got it going on here. This is what we're supposed to be doing with these. We've got this digital capacity. This is the way of kind of bringing all those things together.
So when you're in the building, you won't know that there's one, whatever type of fixing it is, that goes down that holds that on. But you can see that ring beam, whatever you want to call it, sitting on top of the diamond. And so that idea that it's legible, that you actually recognize that one is different from that one, and they join together. That's very important to understanding how a timber building is made as opposed to a concrete building or a steel building. So that's all part of the message. So you can see that the process of doing this was a lot of fun, but it was also relies on everybody on being on the same kind of approach.
Yeah. So we kind of kept things simple for ourselves. So the floors are just LVL beams and CLT floors. So that's nothing more than beam and post construction. So we gave ourselves call it an easy win there. If you like to do something that's normal and been well tested, all of the joints are slightly housed and then pinned with diagonal screws. So we haven't got bracketry or joist hangers. So we've gone that far to make sure that all the joints are calm. That's just timber on timber that you see. That's something. Making joints calm sounds great architecturally. It's the harder thing structurally. Once you start to get in the rhythm of the right thinking process for how to put the joints together, and really once you've done it a few times, you kind of get back to it. It's actually just what a builder would naturally do. You want to put a bit of a housing in to sit it on when you're building it, so it lands on something, and then you want to hold it together tightly once you've landed it on, and so then you pin it with a screw. And often screws put in diagonal from the top down are the easiest thing when you're standing on site. So we've got these great technologies that we've got from Italy and Germany and Austria now with large fully thread and part thread screws. So it's just a matter of getting new detailed types. We're starting to grow a library of detailed types that steel and concrete have had them for decades, and we're kind of getting them for ourselves a bit now. So yeah.
In the same way that in anything architecturally, making something look simple is actually quite hard. You can apply the same thing to making something look calm. It's the same thing. Particularly when you live in our earthquake-prone islands, so calmness is quite an interesting word.
Yeah, no, I forget who said it, but there's like someone who said that writing a small book's much more difficult than writing a big book. Probably a similar thing when it comes to architecture in that sense.
Yeah, it's interesting. We in our office, we're finding that going to furniture and joinery and that sort of thing, looking at the detailing of that, and then upscaling to structural scale has been good. We've used a lot of epoxy in the past for threaded rods and that sort of thing, but we're doing more like anchoring and pinning, putting pins through and confining pins, using a lot of we call them wood stirrups. So you're screwing perpendicular to the grain and confining it from splitting, and thinking of it in a different way of detailing, rather than, it's not components. You have a component, then you clamp it together so it's not vulnerable to splitting, and then you can make these connections out of it. It's kind of a different mindset, but because you haven't got your habitual kind of plates and cleats that you kind of go to as a structural engineer. So it's kind of fun, when you do something new and you get it to work on the numbers. That's what us engineers live for, right?
Yeah, and if we spun all this back, back to the kind of this idea of what this node gave us, this way of making the load continuous, is, and I'm going to talk great generalizations here, but that normally steel or concrete is about the same size or a bit bigger. Well, the timber is a bit bigger than steel or concrete. So just say on a normal 3-story high building like we've done in the past, it might be 500 millimeters square for a column size. So here it's 300 by 90. So the actual timber size is less than a quarter. And that's really interesting because, if by having less timber, the timber's easier to resource, to fabricate, transport, erect, change. And so that's hugely interesting in itself, that as an approach, and we're interested in if we can make things smaller, to actually have less mass, as opposed to mass timber structural buildings, as the name suggests, being bigger. They can be smaller, then the process actually gets more iterative and kind of gets easier, easier to manage. And that's quite an interesting story. And so this building's carbon neutral on day one. And there's two interesting things about it. One is that all the timber in the building's grown in New Zealand in the next 35 minutes. So that's a renewable resource. And New Zealand doesn't have, we've got limited concrete and limited steel. And we're a long way away, and if it's coming on a boat, it really is coming on a boat. But we have renewable timber. So that's really interesting. And the other thing is that I spoke at a kind of a conference out of Florida in the UK, and the person speaking before me kind of said we couldn't lower our carbon footprint because we had a concrete foundation and we had a curtain wall glazing system. And this building has got a concrete ring beam foundation system because of the geothermal, as Alistair spoke about, and it's got curtain wall glazing all the way around. So, and it's carbon neutral on day one. So what it means is you can do it. You can do it, and even if you're not getting to carbon zero, you're getting to carbon better. And that's really important, right? That this is what this is allowing it to do. So even with a smaller timber size, this building's still carbon zero on day one. And so that's an invitation in itself for everyone to kind of think about what that means.
Yeah, it's a big deal that it can happen straight away, and that the world is focusing more and more on embodied carbon. So yeah, there's a real solution on the table. One of the things, Alistair, you mentioned before was that you did the modelling up until LOD 500 yourselves, and on some projects this can get pretty messy, especially when you've got multiple timber suppliers and steel fabricator sort of coordinating all the models and everything like that. So do you think that it's the lead project engineers, best sits with them to do the modelling for LOD 500, or what do you think?
Not right across the board. Like we've got some simple gang nail trusses that hold up the roof, and we just, that we documented them normally. It was really the 3D sculpted details that we did to that higher level. So we did it where we needed to, and we didn't where we didn't need to. So we probably using your judgment to do the right level of detail to make sure you understand it, I think is the trick. And don't be afraid to draw it. I think a previous business partner of Jeremy's said, if you don't draw it, you get what you deserve. I think I quite like that quote. Because there's nothing, we haven't seen this stuff before, so you can't see it unless you draw it. And I think sometimes engineers get you got to sit with your drafty and play around with it and move the screws around and bring them. And I found that you get the whole office, you get someone standing over your shoulder, and all the cheap seats start making different comments about how it could better fit together. But that's good stuff. That's how you kind of get the new ideas happening. And everybody has fun because you can only design so many fin cleats with 4M20 8.8 bolts in your life as a structural engineer before you kind of have trouble staying awake after lunch. So it's good to do some of that, and I think it's the diving into the detail, bring it up again, have a good look at it, spin around, are we doing the right thing, chat to the timber fabricator, they go, yeah, that's all very well, but, and then complete the loop, and you get something you're all proud of.
I mean, at our end, we're modelling, well, on prior buildings we would have modelled every single stick, because they were kind of stick buildings, and this one's kind of more of sort of elements. But right from day one, we're modelling in 3 dimensions every timber element in the building. And that's a discussion between us and Alistair and Dunning Thornton and the service engineers contributing and all sorts of things. But effectively what it's doing is it's allowing us to simplify it. So we're continually updating our system as Alistair, improves and prompts and, and I think
that helps us because it means we don't have to do so much up front, but then we can do more work at the back, and we've got the fee and the drawing time to do the refining process. Because sometimes, if you commit too early, the engineer starts getting grumpy and goes, "I don't want to do another iteration. Like I've already spent my fee." So it's about having people you're used to working with, engineer architect, to get that flow going well. If we're going to nerd out about the BIM for a while, what's quite interesting. The Anthony Gardner at ours, our BIM manager, drew this and scripted all the diagrid in using Dynamo. And it's slight. First of all, you think, oh, is that slightly unnecessary? It's pretty regular. You could just draw it. But the beauty of sometimes doing that is that it either is 100% right or it all breaks. And so you can start to rely on the model. If it's defined mathematically, it's either 100% right or it's obviously wrong. And we've used that as a technique sometimes for this, where you've got complicated 3D structures, and it's a way of injecting a checking discipline, but you're checking as you're making rather than checking afterwards, because sometimes it can be pretty hard to check these models. And a little bit looping back to the earlier discussion, if the engineer doesn't draw enough, the person doing the shop drawings has too big a job and it's too hard to check everything, because there's a lot to think about with mass timber buildings. We've got to think about the gap tolerance, and that's different perp to grain versus longitudinal to grain. How are you going to have tolerance to slide something past each other as you fabricate? These diamonds needed to be let out a little bit to let the floors drop in and pulled in a bit on site. So that was a few long chats with the contractor about that, but we got there. XLAM did a great job of helping the main contractor erect all the timber elements so that they could bring their mass timber experience, to that. And it goes right through for the, understanding that, you can't put a acro prop with a rusty bit of steel on the piece of wood, because if you do that, it'll make a rust stain and everybody will hate it for the rest of the life of the building. There's all sorts of things to think about. So, us at the design phase need to do our mahi work early on so that, gives the rest of the team time to kind of do their bit.
Even going back to the really simple things, and I can't remember exactly what the number is, but I think it's 4 meters. Is that right? The diagram, the grid is 4 meters.
4 and 2, and we just kept it simple. It's all 4 meters. No 3.95s. No, it was 4s and 2s, and
really round. It's really round numbers. We locked in the grid really early, and there was a really important moment where we said to everyone, "This isn't changing." And so, because if we changed one little thing at that point, then I just imagine how many loops was going to go on in Alistair's world. It would have been a disaster. So, little things like that too. Are we all happy? Are we all agreed? Nice round numbers. Okay, off we go. So usual things you do, but they become more important in this kind of building.
Yeah, no, that seems like a big deal. Those little things definitely add up. It's been so good having you both on the podcast. We might just do a round of lessons learned from the project, starting with yourself, Jeremy. And I mean, you can talk really an open-ended question if you want to talk about some of the, how you made innovation a success, or just lessons learned and the challenges you had in general, which we haven't really spoken about yet.
There's lessons in everything, aren't there? I think the thing that we are interested in, and we do a bit of teaching at the University of Auckland, which Alistair comes and helps us with, which is wonderful, is that if you actually want to do something new, you actually have to want to do it. So you have to want to help, and that's really what this whole point is, to try and help outwards, to try and encourage people to do timber buildings and make it more kind of achievable, and show where someone has to do it first. And if you want to do something new, you have to ask questions. And so I think it's really important. I know the silly question we asked at some point of, how do we make the timber smaller, led to a discussion about if the timber follows the grain, it's like a tree. You know, and that's really important, right? Like they're really important moments, because you ask the question, then you have to start to solve it, and you can start to solve it. So my sort of thing on all this is that, you know, we should all be looking to help outwards as architects or engineers or whatever you do, right? Or wood makers. And that's the first thing, right? How do we help? And I'll just kind of finish with I got asked at this conference once, what was the biggest lesson to learn from all this? And I kind of said to them, you've got to remember that the young generation, they're all over climate change. They're all over how good timber is. You ask a 5-year-old, they know. The biggest thing to get your head around is that it's our generation needs to keep up. We need to keep up asking questions and keep up facilitating ways that they can keep moving. So, and I think that's a really good way of looking at it. Yeah.
Wonderful. And yourself, Alistair?
Probably I'll dwell on two things. One is that I think us structural engineers are learning a lot, and we've got to be open to learning and not all saying we know all how to solve these. And I think different firms, there's a few groups of us who kind of publish these buildings and talk about it and share, because I think that's good for all of us, because it's tough, especially tough in New Zealand. Our timber code, even though it's published in 1993, is actually the 1986 code. So most of the people who are doing really great timber work weren't even born when our timber code was written. So that's a big crutch, but that's being solved with a joint New Zealand-Australian standard. But I think the biggest lesson is try and use timber everywhere, but there are some places where you've got to put the right material in the right place. Where we've got CLT inside, where the front arches, the front entryway is, we've got treated glulam outside that's got a break to the CLT, and then it's got some beautiful carvings, CNC carvings that were put on the outside of that. So making sure you choose the right material in the right place. And there's a couple of cheats in the building, which I'll put my hand up for. One is that there's the atrius sails right across the front of the building. Looks like nothing's holding it up, but there's actually a steel walkway that you walk on. So it's just some, scaffold plank type metal, but we use that as a beam to kind of hold the walkway together. And the same at the bottom of the glass balustrade on the stairs is actually the plate that the glass is screwed to helps the timber stairs hold together, because timber's not good at turning corners. You've got to glue it up and laminate it up and do all sorts of hijinks. It's not like you can just bring two things together and weld it like you can with steel. So doing good timber stairs, I think, is a learning curve for us all. We've done some reasonably impressive steel with a little bit of sleight of hand with timber, with a sleight of hand of steel on these on Scion. But I'm looking forward to some new forms of stairs that'll come out of these sort of mass timber buildings.
Well, thank you both of you for so much for coming on the podcast. It's been wonderful. This project's won all the awards all around the world, and rightly so. It's phenomenal innovations that you've both put together. So we'll leave it there, and thank you again.